Okay, let's get started. Welcome to motion planning lecture number 13. Hello. And today we will talk about multi-robot motion planning. And I think this is one of the most interesting topics in the course because multi-robot motion planning, we finally go to very high-dimensional spaces. And all the planners which we have seen so far as I'm aware of, are not able to solve those high-dimensional state spaces. And so we will look at different approaches of how you can even find feasible solutions in those high-dimensional state spaces. Okay, and before I go into that, I want to just recap briefly what Wolfgang talked about last week. We talked a little bit about optimization-based planning, especially COMO, and then also a little bit of comparison of search optimization and sampling, and also some hybrid approaches. As I said today, multi-robot motion planning, and if we are still having time, I will also talk a little bit about planning with manifold constraints. This is something, for example, where robots make contact with the environment, or where your end effector of the robot has to stay on a surface, for example. Okay, but let me start with multi-robot motion planning. So why is that actually important? Of course, if you want to, for example, control a large fleet of cars, then of course you need to coordinate the movements of the individual cars, and you need to make sure that they're not colliding with each other, so you need some kind of multi-robot navigation. Something similar happens in factories, where you have multiple robots which are simultaneously working on, for example, a workpiece, and so those robots should, of course, not collide with each other, but still they should solve something as efficiently as possible. Then, of course, for example, if we have assembly tasks where, for example, robots have to assemble a small building or something, then, of course, the robots have to work together in some cases, and also they have to not collide with each other or the environment. And, of course, if you have a large fleet of drones, multi-robot planning becomes important, because now you also want to control them all and not collide with each other. Okay, and the definition of multi-robot motion planning is basically that you want to coordinate the motion of multiple robots, and they are all acting in the same environment. And those robots could all be different. For example, you have fixed manipulators, you have some drones, you have some cars, you have humanoid robots. You have, whatever robot you want. And I would say the main central idea in multi-robot motion planning is that planning is just normal, standard, classical planning, but this time in the composite configuration space. And so, for example, if you have 3 robots, and those 3 robots have 3 state spaces, x1, x2, x3, then the composite state space is just the Cartesian product of those 3 state spaces. And now the question becomes, do we need to adjust some of those primitive methods which we have used for classical planning if we have this composite state space where you have just the Cartesian product of 3 different robot state spaces? Does anyone know what we would need to change? For example, if we look at those 4 methods here: sampling, interpolation, propagation, steering for the kinodynamic case, and collision checking. Yeah.
Collision checking, of course, because like the robots would collide.
Yeah. And what about the other 3?
Well, I guess the sampling process would still be the same. But if you want to interpolate between sampled points, you would have to do that 3 times, like for each robot separately, I suppose.
Exactly. Yeah. The same basically applies to propagation. You would have to do it separately for each robot. But usually in those primitive functions, you do not check if something is valid. And that is why you don't have to actually change those 3 functions at all. You can just do them individually and then just combining them to the Cartesian space. And only collision checking, so you have to do collision checking of each robot to the environment, and then on top of that you have to do collision checking of each pair of robots if they are in collision. Right, but otherwise this is just normal standard planning in the composite configuration space. However, there's a big problem here, namely that we already heard in previous lectures that computational complexity of motion planning is usually exponential in the number of dimensions. So this means every time you add dimensions, your runtime of your planner becomes worse and worse and worse. And so, of course, if you have a composite state space, you have a very large number of dimensions, then planning is not practical anymore. And we need to find different approaches. And so one big goal of multi-robot motion planning is to find good decompositions of this composite configuration space, such that we can make multi-robot planning more efficient, while, of course, also keeping completeness and optimality. So that is basically the main goal, that we want to really figure out what are the important regions in our composite configuration space, where do we need to plan, can you do some simplifications there, and so on. And that is all what we want to do here in multi-robot motion planning. Let me just close the window. Okay, and before I go more into details, I just wanted to give you a broad overview about some of the categorizations which people make in multi-robot motion planning. So I would say the biggest one and the most important one for planning is the question of if all your robots are identical. So if all your robots are identical, we call that a homogeneous motion planning problem, and if they are not, then it's non-homogeneous. And as we will see later, if all your robots are equivalent, then we can do some very smart reductions and do very efficient planning. Then also the question if they are the same, the robots, if it's a homogeneous problem, are the goals interchangeable? So this brings us to labeled versus unlabeled motion planning. And then also a question, who controls your robots? So you could have one centralized entity which controls all the robots, or it is more decentralized where some or all the robots are actually controlling themselves and moving themselves to the environment. And then on top of that, you also want to know what kind of cost do you want to minimize. So there are two classical costs which are considered in multi-robot motion planning. One is make span, which refers to the last arrival time. So you have a bunch of robots and you want to minimize the arrival time of the slowest robot in your team. And sometimes this is not enough, because maybe you have one robot which is super slow and then the other robots can just move around in the time, and you want to also optimize their time. And so something which you could do is to introduce flow time, which is the total arrival time. So basically you just sum up over the arrival times of the individual robots. So those are the two main ones which are usually used. And today I want to go more into detail about homogeneous and non-homogeneous planning, because this is basically the main topics for motion planning. So homogeneous planning, I want to talk about pebbles on a graph, which is a very nice reduction, and then I want to talk about conflict-based search of how we can solve this. And then non-homogeneous planning, I want to show you two approaches, one prioritized planning, one decomposed planning, and then we will look at two algorithms, M-star and DRT-star, which I would say are the most influential ones in multi-robot motion planning when all the robots are not equivalent. Okay, so let me start with homogeneous planning. So homogeneous planning, as I said, all your robots are equivalent. So maybe you have a set of submarines which you want to control, or you have multiple drones, and they are all from the same company. They have all the same measurements, and they're all equivalent. And in that case, if all your robots are equivalent, all your robot state spaces are also identical. And I wrote here modulo robot-robot collisions. So basically, all your state spaces are equivalent. But on top of that, of course, you have to make sure that your robots are not colliding with each other. And because those state spaces are now identical, we can reduce this problem to something which we call pebbles on a graph. And to do that, we assume that we have this homogeneous team, and we say, okay, let's say we have M robots. that means that we have a composite state space of m times x, where x is the state space of an individual robot. And yeah, to just show you this, I want to give you a small example in 2D. This should already explain how this pebbles on a graph reduction works. So let's say that we are in this environment here. I think you saw this already multiple times. So those boxes here, they are obstacles. Green is the start configuration for a point robot, and red is the goal configuration for a point robot. But now we have two robots. So one is starting here, and the other one is starting here. And this one wants to go to this red point, and this robot wants to go to this red point. And because those robots are identical, they are both point robots. They have the same state space because the environment is also identical. And what you can do now is that you just do sampling in one of the state spaces, and you construct a roadmap in one of those state spaces. And because those state spaces are equivalent, what you could theoretically do now is that you just copy-paste this roadmap into the other state space. And if you have 100 robots, then you can just copy-paste it theoretically in all the state spaces of the other robots. And what this actually enables you to do is that you can now take a new state space here, which I call Z, and you just copy-paste this roadmap into the state space, and you copy-paste also the start configurations and the goal configurations of your individual robots. And then you connect them to the roadmap. And so this is very similar to what you did with this probabilistic roadmap approach, but this time you actually connect multiple robots to this roadmap. And now you basically reached the point where you have a different problem, which we call pebbles on a graph. And so the idea here is that now you want to move those two robots from the green start configurations to the red goal configurations. And pebbles on a graph is basically defined as move m pebbles on a graph from a start arrangement to a goal arrangement. And pebbles are, of course, not allowed to collide. So this is actually a very well-known mathematical problem. And because now we have only one state space, you have basically reduced the whole problem of, I don't know, m times n, whatever n is. For example, in this case here, 2. You have reduced everything to just one state space, and you only plan in a state space of, in this example here, 2 dimensions. And so, as you know, planning in lower dimensional space, of course, much more computationally efficient. And so the only thing we have to do is solve this pebbles on a graph problem. And in general, this is much easier to do than just planning this whole huge composite state space. So yeah, this is the main idea. Let me give you a little bit of theory on that. So yeah, just to write down what I already said in this example. So we assume that we have this state space, this composite state space consisting of m robots, each with a state space x. And we have start goal pairs for each robot. And then the idea is that you create a single roadmap G on x, and you add all your start and goal pair vertices to x and connect them to your roadmap. And then you solve this simultaneously while taking, of course, robot-robot collisions into account. So this is basically just the same what I just said in the small example, just a little bit more generalized. Okay, and here again, the definition of pebbles on a graph. So you have this graph here on x, and you want to move m pebbles from start vertices S1 to Sm to goal vertices G1 to Gm. And there are multiple approaches to pebbles on a graph. I just wanted to mention here 3. One, push and swap, integer, linear programming, and conflict-based search. So they are all good approaches to that. Today, I just wanted to focus on one because it's, I would say, the most widely used one for this problem, which is conflict-based search. Before I go into that, any more questions about this general reduction from the states, from this composite state space to just one state space and to this pebbles on a graph problem? Or is that clear? Okay, cool. Then let me just show you how you can actually solve this pebbles on a graph problem using conflict-based search. Okay, so first some assumptions. So we assume that each pebble has two moves. It can either wait at the current vertex or it can move to an adjacent vertex. And the goal is to find a set of moves to reach a certain goal arrangement. And of course, you want to do that optimally. And the key idea of conflict-based search is basically that you resolve collisions one by one. So first you just plan for each pebble individually. So you just assume, okay, I don't expect any collisions. I just want to move them on the shortest path to the goal. And whenever there's actually a collision occurring, then I will do something about this collision. And so the strategy to do something about the collision is the following. So we assume that there are two pebbles A, B. They collide at time t at vertex v. And then we add this as a constraint to our problem. And we basically add either one of two constraints. So either we say, okay, A should not be at v at time t because there's a collision. A should not be there. Or we say B should not be there. It's v at time t. And this creates your constraint tree because now you have this bifurcation into either A is not there or B is not there. And then you just continue on this constraint tree. You try to solve the problem. And you pick the next entry based on best cost and first collision first tiebreaker. Okay, so this is the general idea behind it. And to just show you how this actually works, I brought you here a small example. So we have here a problem where you have 6 boxes and we have 2 robots, a green robot and a red robot. So those are just small disks. And they can be in one of those boxes here, in one of those 6 boxes. And the goal for each robot is to reach their goal region. So the green robot should reach the green goal region. The red robot should reach the red goal region. And of course, as you can see, if the robot just move on a straight line, they would never actually accomplish this task because the red robot just blocks the green robot. And now we want to do constraint conflict-based search to resolve this. And so the idea is basically that you start here in your first iteration. You just plan for each robot individually by just assuming, okay, the other robot doesn't exist. And so this would give you the shortest path for the green robot, which is just a straight line, and also for the red robot, just a straight line. Then what you do is you compute the cost. So in this case, 6 for 6 moves of the green and red robot. And if you just execute this, you suddenly find, okay, there's a conflict at time equals 3. So this basically happens, the red robot moves to the goal at time equal 2, and then the green robot arrives there also, but at time equals 3, and so there's a conflict, of course. And as I said, you can now add constraints so that either the green or the red robot is not at this point here at time equals 3. So this gives you 2 different new problems. So one is where the green robot is forbidden to be at the goal region here of the red robot. Then you do the same again what we did in the beginning. You compute the shortest path with the constraint enabled. So this gives you here a cost of 7 because the green robot just decides to wait once more so that it is not here at the goal region at time equals 3. And then you just have postponed the conflict to time 4. And the other possibility is that you restrict the red robot to not be at the goal region here. And this gives you also a cost of 7, but now you have a conflict at the second time step. And so you have now two constraints, 2 problems, and you have both with a cost of 7 and a conflict of t equals 2 and t equals 4. And because we said we use this tiebreaker of first conflict occurring earlier, we take the second one here, and we again add 2 constraints. Either the red robot is not at this position here at the second time step, or the green robot is not there. So when we start with the green robot just waits here one step more. We have a cost of 8 and a conflict at time step 4. And in the other case, the green robot just moves towards the goal because there is no constraint here. But the red robot has 2 constraints. It should not be here at time equals 3, and it should also not be here at time equal 2. And that means that the red robot just moves out of the way. And if you just execute this, you see that there's no conflict, and you just end up here with a solution which has a cost of 8. So that is the general idea of this conflict-based search. And you can apply this to any number of robots you want, and this solves you the whole problem. And something which I have not talked about is that this solution which we got here is actually the optimal solution. And to show you that this is actually the optimal solution, I just wanted to give you a small proof sketch of this. So we have this theorem here, conflict-based search returns the optimal solution. And there are 2 parts to show this. One part is that we prove that no valid paths are removed by conflict resolution, by this bifurcation of constraints. And the second part is that we prove that a goal node path has actually the lowest cost. So yeah, let me just very quickly go over those 2 parts. So the first part, for that I will just introduce some notations here. So I will say, okay, we will have open nodes, which are in gray, and we will have closed nodes in white, and we will have goal nodes marked with a G. So this is basically the same here as we had in the example. And how we solve it is basically by doing a best first search over this constraint tree. And so the proof that no valid paths are actually removed by conflict resolution goes as follows. So first we say, okay, n is a node in our constraint tree, and CV of n is all valid and consistent paths at n. And if we add a constraint at our node, we split those nodes into 2 new nodes, n1 and n2. And because we know that we have applied a constraint which has just resolved in invalidity in our problem, we know that a valid path needs to be either in n1 or n2, or if it's not there, then of course it needs to be invalid. And therefore, we can say that this set CV of n is actually split into 2 sets, one for the one node and the other one for the second node. And so, yeah, basically nothing happened here. All the valid paths are just splitted here, and all the invalid paths are removed here, because this constraint which we applied is basically a constraint which only removes invalid paths. So this is the first part, and so the second part is that we want to show that the goal node which we have reached now has actually the lowest cost of all possible paths which we could reach. And so for that, we just assume that we reached our goal node and we have a cost of C of G. This is the first step. Then the second step is that we just take an arbitrary path, which is valid, which we call P. And then we know that P must be in an open node N because of the first part, because it's valid. And then it is also lower bounded by the best cost at this node, which we call C of N of P. And because we also used best first search, the cost at G must be the lowest of all open nodes. And therefore, we can have this inequality here where we have just taken a valid arbitrary path, and this has to be greater than all the paths which of the best path at its specific node. And this one has to be greater than the cost at the goal node. And so this basically shows you that the lowest cost is actually attained at the goal node. And this shows in turn that we reached an optimal solution. Any questions about it? Yes.
You basically said that it can wait at different points.
Mm-hmm.
Is there
Sorry, again?
Is there no option that it also waits at the start configuration? Because you said the only option for it to not be at that point for T3 and T2 would be to go down,
Mm-hmm.
but it could also just wait where it is.
Yeah, so basically what you do is that you just compute a star shortest path search over the graph, and of course that could also entail that you wait at the start configuration.
Okay, so that could also be another
Yeah.
thing on the tree.
But I think in this case, the shortest path, I would say that this is actually the same cost as the path which I showed, if you just wait at the start configuration. So I think a star would just return you one of those paths.
I mean, it's not it's not the optimal path and it's not a valid path, but like we waited at like the one point and then the next one, and
Mhm.
but it could also be an option that you wait at the start configuration.
Yeah, so I think it would be the same cost, and so that is why it would also be an optimal path. And so in this case, yeah, a star would probably return you one of them. I don't know which one of them it would actually return, but in the end it should not matter because they are the same cost. So yeah, but definitely possible. Yeah. Okay, any other question? Yes.
In the case in example, we have no state in the below flight, then there is no solution, and will the algorithm terminate? Or when?
Yeah, exactly. So if you don't find the shortest path on the constraint with the constraint enabled in one of the boxes here, then you get no solution if, of course, all the other boxes have also no solution. Yeah. Good point. Yes.
I have a question. Like, are all these constraints applied globally or just for the subtree? Because, like, I think it's feasible that if I have like two paths to a goal, and one path I will have a conflict.
Mm-hmm.
And I will, maybe like this is the optimal path for one robot, so both want to go there and they will have a collision here. But eventually these paths meet again and there will be another constraint. So like the other path that might be useful for one robot to take would then never be taken if it's a global constraint. But like if it's just a constraint for a subtree, then this would still be possible, right?
So those are definitely global constraints for the whole graph. So I'm not completely sure where you are trying to get at.
I think my point is that if I have two completely different paths for
Mm-hmm.
a robot to take,
Mm-hmm.
and they intersect maybe at some point,
Mm-hmm.
then like the constraint is just that they can't collide at a certain point.
Exactly.
Yeah, okay,
And then this is just factored in the next shortest path search. Yeah.
okay, never mind.
Yes.
So like the constraints are specific to a box in this tree and its children, right? It's not for the whole tree.
It's not for the children necessarily. So it's just a graph. So it could also be that there are some cycles. So
No, I mean
yeah.
this representation of the constraint
Mm-hmm.
tree.
Mm-hmm.
The constraints are only added to like elements of this tree and its children.
Oh, you mean the children of this tree here? Yeah, exactly. Yeah. Okay, cool. Then let's actually look at a small example. So here I have a picture and I will also show you a video shortly. So we have here an example of 32 drones and they are on a composite state space which would have 192 dimensions. So this would definitely be unpractical to plan in. However, if we do this whole thing which we just talked about, reduction to pebbles on a graph and conflict-based search, we can actually solve this in roughly 60 seconds. And for this example here, we have computation time of 50 seconds for generating actually the roadmap on R6. Then 0.8 seconds for conflict annotation, 0.5 seconds for conflict-based search, and then additional roughly 6.5 seconds for optimization, a bit of smoothing and shortcutting of the paths. And here's a small video. So this is actually from research which Wolfgang did in 2017, and where he applied this whole reduction to pebbles on a graph plus conflict-based search to solve a very large multi-route motion planning problem. And you can see here all those drones are coordinated at the same time, and they are not colliding with each other, and they are faithfully reaching a goal arrangement. So this is basically what you can do by using homogeneous search, pebbles on a graph reduction, and conflict-based search. Cool. Any more questions about homogeneous motion planning before we wrap it up? Yes.
Do you know the specifications of the machine for the computation times, like the 50 seconds?
Not out of my.
Okay, but it was probably not a laptop, right? You know that?
So, I mean, it's of course in the paper. You can just look it up, but yeah, I would actually think it would be a laptop.
Oh, okay.
Yeah. But yeah, no guarantees. Yeah. Okay, any other question? Okay, so that's wrapping up homogeneous multi-robot planning. So if all the robots are equivalent, great, you can just reduce them and everything is fine. Now we come to, I think this video is still running. Okay, so now we come to our next topic, which is non-homogeneous multi-robot motion planning. And so now we are actually at a case where you can't do this reduction anymore, because now all the robots are not equivalent anymore. You have maybe some manipulators, some drones, some cars, some humanoid robots, whatever, but they are all not equivalent, so all the state spaces differ. And you have to actually think about other approaches to that where you don't have this reduction anymore. Yeah, and because there's no easy reduction possible, you can actually not efficiently solve it in the composite state space, because, of course, all the state spaces differ. And in terms of approaches to this problem, I would say there are two really big ones, two main approaches. One is a prioritized approach, where you basically first, so this is basically visualized here on the left. So the idea is, if you have this whole composite state space, what you do is you first plan just for one robot, and once you have a path for this robot, you use it as a constraint for planning with 2 robots, and then you use this as a constraint for planning with 3 robots. And so in my mind, this is like a vertical decomposition, so I sometimes call this vertical, but so usually this is called prioritized. And another approach is something which is called decomposition, where basically you plan for each robot individually by ignoring robot-robot collisions. And once you have a plan for each of the robots, you just try to combine those paths all together to find a solution for all of them. So those are two big approaches which we will talk a bit about. And I wanted to start first with prioritized multi-route motion planning, just to give you a small, quick visual example. So what we have here are, again, like some small state spaces of a point robot, which needs to go from green to red. And the state spaces here, the 3 ones on the bottom here, they are basically the composite state space. And what you do with prioritized planning is that you first find a path for the first robot, and then you use this path here as a constraint for the second robot. You plan a path now for the second robot. Then you take those 2 paths again here as constraints, and then you plan another path for the third robot. And so the state spaces here all differ because those are all different robots. So they might be in the same environment, but of course their state spaces will look different. Okay, but this is the general idea. And we will look now at the most simple case, namely that we have just two robots. We have a composite state space, which I call X, and it factors into Y and Z. So Y would be your first robot, Z would be your second robot. And so prioritized planning for this case would be just that we find a path on Y and then use it as a constraint on X on the composite state space. And so how do you do that? You can actually do that by a concept called a path restriction, which is actually the way of how you model paths from one of the spaces as a constraint on the full space. And for that, let me give you a small example of two 1D robots with a state space S1. So we have here two robots which can just rotate here around this point, and they have both this line segment here, and this could be maybe something from a motor or from a factory, and you want to move them in such a way to go from one start configuration to a goal configuration. And small question, so what would be the composite state space look like for those two robots? Anyone an idea?
Would be two like values. It should be vector.
Yeah, but so what would be the structure of the space? So basically the single spaces would be S1, basically a circle where you can just rotate around here. But if you just take the Cartesian product of those two circles, what would you get?
A torus.
Exactly, yeah. So basically, if you want to plan here, then it is planning on a torus. And this basically is the same as you would also do in the 2D case. You just sample on the torus, you connect edges to samples, and then you get a shortest path here from one position to another position. Okay, and now we want to do prioritized planning. And one way to look at prioritized planning is as a projection from this torus down to one of the robots. And so this would be, in terms of the state spaces, a projection from the torus down to the circle. And so if you have a path on the circle, then this induces a constraint, and this constraint is modeled as a path restriction. So what you can see here is the circle. We have green and red are start and goal configurations on the circle, and this white line here is a path. And this area here are all the points which, when we project them down, they would be on the path. So that would be basically the constraint imposed by the path on the circle. And to just say this a bit more formally, so we have this composite state space X, and we have a projection from X to Y. And in our case here, this projection would just remove one of the coordinates. So we would just project from θ1, θ2 to θ1. And in this case here, with this projection, we often call Y also the base space. And the path restriction is basically defined as follows. So first of all, let's talk about what a restriction is. So let's say we have here X, and we have this projection pi. And now if we have a subset U of Y, so Y is the lower dimensional space here, then a projection is defined here as the inverse of the projection defined on this subset U. And so this definition just means that we just want to single out all the points on the whole state space, which when we project them down, they will be on the subset U which we have chosen. So this is the general idea of a restriction. And a path restriction is basically a very specific one where you have a path on this lower dimensional space, which we usually call P. And then you compute the image of this path, which is just a subset of your lower dimensional space. And then the set, the inverse of pi of this path is called the path restriction. And yeah, intuitively, this is basically just all the points which, when you project them down, are on this path here. I think this is the main thing which you have to remember about it. And all the constructions here, they are just to make this a bit more formal. Okay, and so now what can you actually do with such a path restriction? One thing which you can do is restriction sampling. So let's say that we have this torus again, we have this projection on the torus, and we have a path on our space S1. So this path is basically just a solution to one of the robots. And then we can just go up here to our composite state space, and we can just sample first an element on our path here, and then we single out an element of the inverse of this projection here on our state space. And what you can see here is, if we do that, then we just plan in this restriction here on the space, and we just find a solution which is lying exclusively in this path restriction. So this is the whole idea of this prioritized approach. And then, of course, there comes the question, is this actually probabilistically complete or asymptotically optimal? Does anyone have an idea?
I don't think it's complete because we can't guarantee that the first robot that moves blocks the paths of other robots.
Yeah, exactly. So this is not complete, and by that, of course, also not optimal. It is, however, widely used because it's a very fast way to compute paths if there are actually paths and they are not blocking each other. However, if you want to make it complete and optimal, that is possible, but it requires two big changes. One is that you have to replace this path restriction with something more general, which is a graph restriction. And you need to also continue sampling on your base space. So this is, for example, a case where you don't have only the path on your circle here, but you have basically computed a graph or roadmap here on your circle. And then for each of the edges, you compute this restriction here, and you get some shape like that. And so those are all the regions which, when you have a point in one of those regions and you project them down, you will be on the roadmap here of your lower dimensional space. And those are actually regions which are more important for planning, because you already know that you got a solution here for the first robot. And so in turn, this acts a little bit like an admissible heuristic for your original problem. Right, and so one way of how you could plan with that, so in a classical setting, what you would do if you have just paths, you would just take as input here a start configuration, and you would take also as input x1 to xk, which are just the spaces for one robot, for two robots, up until k robots. And then you just iterate from 1 to k, and you grow the space for xk, and you get a path from xk, and then you set this as a path restriction for your next level. And you do that basically every time you have found a solution, and that is how you do this, I would say, greedy prioritized planning. Another approach is that you actually continue sampling. So basically you also iterate over all the spaces, but this time you have also like a priority queue here, which is called Q. And while you're not terminated on one of the spaces, you just select one of the spaces from your queue, you grow it, and you push it back to your queue. And so this one is basically something where you can actually prove that it's probabilistically complete, and you can also extend it to make it asymptotic optimal. So those are two ways of how we can do prioritized planning. And now let me just show you a small video of how this looks like. So here we have a prioritized approach where you first plan for some of the robots and then for all of the robots, and you can solve very large state spaces with that one, where basically, for example, here all the robots have to go from one side of a circle to another side of a circle. Of course, in this case here, we have all the robots being equivalent, but of course, the algorithm is general enough to just do the same here for robots if they would be like different from each other. Okay, any questions about this prioritized planning approach? Okay, then let me give you just a small advantages and disadvantages of prioritized planning. So advantages are definitely that paths and graphs on your base space can be seen as necessary conditions on your solution. And so if you think about this a bit more, then this is actually very similar principle as what we had with admissible heuristics and A star. So this is basically a good way to solve very complicated problems. And it's also pretty fast if robots are near decomposable, which means that robot-robot collisions are pretty rare. Disadvantages, definitely that you have to have some kind of ordering of the robots. You have to say, okay, this robot goes first, this robot goes last. And this is usually not so easy to do. And that basically means it is unclear which spaces to grow first. So there's a little bit of more information which you have to put into the algorithm. Okay, any questions before we move on to decomposed planning? Yes.
Is it like complete? I don't know if you talk about that, but I think it's not, right?
Yeah, so if you just have a path for one robot and use it as a constraint, then it's not complete. But if you continue planning for the first robot too, and you have like growing a roadmap for this robot and you sample this, then you can make it complete. But of course, this incurs more.
The
Yeah.
optimal path for the first priority robot blocks the path for a different robot, then it can't find it.
Mm-hmm. Yeah, so that is why in this case here, you would just sample all the roadmap here. You would not only like take the optimal path on this roadmap, but you would just take any path on this roadmap basically. Any other question? Cool. Then let's move on to our second approach to non-homogeneous multi-route motion planning, which is called the decomposed approach. And so the decomposed approach, just small visualization here. So instead of computing individual paths and then using them as constraint, what you do here is that you first plan for each of the individual robots as if there would not be any robot-robot collisions. So you get paths here for each of the robots. And then you try to combine those paths into the composite state space. You would just take the Cartesian product of those paths, so to speak, and that would give you a path in your composite state space. So this is the idea. I would like to do the same as I did before, just showing you how this works with two robots. Again, we have here X, the composite state space, Y and Z, the individual state spaces. And so with decomposed planning, we would have two projections, one to the first robot, which is from X to Y, and one for the second robot is from X to Z. And then what we do is that we find a path P1 on Y and a path P2 on Z. So those are solutions to the individual robots. And then you compute, again, path restrictions for each of those paths here by just taking the path restriction as we talked about before. And then you define the motion planning problem in this intersection of path restrictions. How does it actually look like on the torus? So let's say that we have two projections, P1 and P2. They go from the circles here on the torus down to circles here for the individual robots. So one robot is basically defining one of the coordinates, the other robot is defining the second coordinate. And then we would compute paths for those robots. So for example, here light blue is a path for the first robot, light green for the second robot. And then you compute the path restrictions. So for the first robot, this could be a path restriction, which is basically just singling out the coordinates here for the robot on the first coordinate. And then you do the second one here for the second robot. You get again a path restriction. And then what you need to do is take the intersection of those path restrictions, and you can now do motion planning in here, which basically means that you move the robots only on this path here. You can move backwards or forwards, and you try to find an optimal solution by just staying on those paths here. And that basically gives you here, for example, if you would use RT, you could compute here an RT solution for this problem. Okay, so this is basically a visualization of how this whole decomposition-based approach works. And yeah, as I said, we compute intersections here of path restrictions, and this is also equivalent to the space of path reparameterization. So yeah, if you basically just move backwards and forwards on a path, this is very similar to what you do with planning on this path restriction. And if you actually search for a path over this intersection, then this is also something which is called path coordination, because you have basically multiple paths and you want to coordinate how fast and in what manner each of the robots is actually executing the paths, and this is basically a coordination on those paths. Again, question, is this actually optimal? Any questions? If you have optimal paths for each of the individual robots? Yes?
No, I don't think so, because we essentially only have a path and then maybe stop or slow down, go backwards, whatever. Like all the other paths that might be only a little bit less efficient, we discard and don't even look at them.
Yeah, exactly. So one of the paths could basically block another one, and then you would be out. And that is why this is also not optimal, but also not probabilistically complete. And again, here you can add completeness by just replacing this path restriction with graph restriction, which brings us to graph coordination. So instead of just computing one path for each of the robots, you actually compute roadmaps for each of the robots, and then you combine those roadmaps together. And so this brings us to a very general recipe of how you can actually solve those problems very efficiently. And this is detailed here. So there are 4 steps. First one is that you compute individual graphs on the component state spaces. Not only paths, but really graphs. Then you consider the implicit product of graphs on the composite state space. Implicit means that you don't compute actually the product of graphs, because this is extremely difficult to compute. And then in the third step, you expand edges optimistically by following the shortest paths on the component state spaces. And this is very similar to conflict-based search, because then in the step 4, only if a conflict arises, you try to do something about it. And in this case here, you backtrack around conflict areas. And depending on how you actually backtrack around conflict areas, we have 2 big approaches to decompose planning. One is M star. It's using a cost to go estimate to backtrack. And then we have DRT and DRT star, and they're using something which is called a directional oracle to backtrack around conflict areas. Okay, so I want to look at both of the algorithms a little bit more into detail. So M star is basically the multi-robot version of A star. It works almost equivalent like A star, but instead of using one admissible heuristic, it tries to use the admissible heuristics of all the individual spaces as the cost to go. So this is really the multi-robot version of A star. and it works also pretty similar to conflict-based search. And here's a small example. So we have here again our two robots, two disk robots, green and red, and they have to again move from start configuration to some goal region here, red and green, and they can only move on those small tiles here. So we have 7 tiles, and on those they can move around. And what we do now with decomposed planning is that we compute a path or a roadmap for each of the individual robots. So you get something like that here, which covers the space. And then M star operates in the following way. So here on the right, you see the composite or the product of the graphs which you computed here for the individual robots. So the top left node here, it would basically be the start configuration of green and red simultaneously, and down here you get the goal configuration of red and green. And what you do now is that you compute the shortest path for each of the robots, which just moves you here along the straight line in the composite graph. And then what you do is you just execute it and you look for collisions. So in the first step, you execute the first step, which means you move both robots here one step down along the shortest path. Nothing happens, no collisions, so you just continue until you come here to the third picture where you have actually a collision, because now green and red are both here at the intersection. And now you have to somehow backtrack, and M star does it in the following way. It goes back one node, it computes all the neighbors of this node, and for each of the neighbors it computes the shortest path towards the goal. This is symbolized here. And then for each of the neighbors you also get the cost to go to reach the optimal, to reach the goal. And you basically just compute this here and you choose the node which actually has the lowest cost to go. In this case, you choose this one here, and then again you just execute the path until you reach your goal region. And so in this case here, you have moved both here to the second step, and then one of the robots just stays here while the next robot is actually moving to the goal, and then the path is free for the remaining robot who moves to the goal. So very similar to conflict-based search, but applicable to a very general graph structure for each of the robots. Any questions about it? Okay, yeah, just to summarize, so M star is actually pretty efficient because it optimistically exploits this implicit graph without actually computing it. And individual shortest paths are actually acting as admissible heuristics from the individual robots, and this is very similar to how A star computes it. And M star is actually combining those admissible heuristics in an optimal way. So it's a very nice way of how you can employ A star as a multi-route planner. And one of the big drawbacks, however, is that it's pretty inefficient for high-dimensional spaces because the number of neighbors grows exponentially, and then you compute shortest paths for each of them, need to compute the best cost to go, and so this is all pretty computationally expensive. And that issue here was really the motivation for the DRT planner and the DRT star planner. So DRT stands for discrete RT, and it works exactly like M star, but instead of computing this whole shortest path and best cost to go, it instead uses an oracle function to pick the best neighbor. And this oracle works only for Euclidean spaces, so you can only do planning in Rn. However, it gives you much faster, a bit more approximate ordering of the neighbors. And it works like this. So, for example, you are at a specific node in your implicit product of graphs, and you have a set of neighbors here, and you want to compute the best cost to go. And the way of how you do it in discrete RT is basically that you compute a random point, very similar to RT, and then you compute a straight line through this point and a straight line to all the neighbors. And you compute the angles between this straight line here to the point and the angles to all the neighboring straight lines, and you just pick the one which minimizes this angle. So in this case here, it could be this one here, and then you just expand towards it. And so this basically combines this random sampling of RT together with this exploration of M star. And this directional oracle basically, just formalized here again. So if we have a vertex V and neighboring vertices and a random point, then this oracle basically computes you the argmin of all the angles between the line through a neighbor and the line through the random point for all neighboring vertices in our graph. So that is the basic idea. And this works pretty well for most cases, and it's much faster than M star. And so I would say this is really the preferable version for decomposed planning. Okay, any question about this one in particular? Cool. Then let me just summarize all the multi-robot approaches. So we first talked about homogeneous planning, where all the robots are equivalent, and we had the superior reduction to pebbles on a graph, which is pretty cool because now we just plan in very low-dimensional space. And we looked at conflict-based search, which is really an optimal way of how you can solve it, and it scales super well with the number of robots. But of course, it cannot be applied to non-homogeneous teams. Then we looked at non-homogeneous planning. One was prioritized planning, where we replaced the original problem with a sequence of simpler problems. And the solutions to those simpler problems provided admissible heuristics to our original problem. However, if we actually use prioritized planning, then we need to specify an ordering. This is usually not trivial, and it can also influence if the runtime significantly. Then decomposed planning was where we plan for each robot individually, which could, for example, also be done in parallel. And then we just combine the solutions in a graph on our composite state space. And if the environment is, for example, static, then the graphs could be pre-computed. And I would say one disadvantage, which I didn't yet talk about, is that the individual graphs generally need to be pretty dense to give good solutions. And if they're not dense enough, then often you can't find a solution. This is just something you have to keep in mind. Okay, so I would say this is everything I wanted to talk about multi-robot planning. Just one more opportunity to ask questions, if there are any. Cool. Okay, so that is all about multi-robot motion planning. And now I want to just switch to a completely different topic, namely planning with manifold constraints. So the idea of manifold constraints is basically whenever you have a problem where you have to make contacts with the environment, your whole state space differs. And so it usually gets pretty difficult to plan in those new state spaces. So manifold constraints, so the basic definition I would say is that you have a constraint on your state space which removes effective degrees of freedom. Examples are, for example, where robots need to make contact with the environment to traverse an environment, where you make, for example, contacts by grasping something, or, for example, where you have to stay with your end effector exactly on a surface, for example, when you want to weld something, when you want to paint something, when you want to wish something. And so this basically removes effective degrees of freedom from your state space. and this is usually pretty problematic to plan with. And this is problematic because it induces zero measure sets on your state space. And that is why I want to first talk a little bit about zero measure sets and what they are. And for that, I want to first start with what is actually a measure. So a measure, or the best measure, what I want to use here in this case, is basically a generalization of a volume. And so the best measure is a very specific type of measure of volume. Namely, it's an n-dimensional volume, and it corresponds to length, area, or volume in 1 and 2 and 3D. And here's a small example. So if you have a 1D planning problem, and you have a point here and you have a line, then the measure of the point would be 0 on the line, and the measure of the line would be 1, because this n-dimensional volume would give you a length here, and the point has, of course, no length. And in 2D, what do you think would be the volume of those three objects here? Yes?
I can square would be 1, and like the line and the point would be 0.
The line would be what?
A line would be 0.
Yeah. And the point?
Would be also 0.
Yeah, that is true. And in 3D, I guess that is also easy. What do you think would be the measure?
Yeah, like the cube would be 1 again, and like all the other.
Exactly. So, yeah, this just gives you a little bit of intuition of how, sets, or the measure of sets looks like here in the common dimensions. And so the best measure basically takes this idea and generalizes it to n dimensions. And basically the idea is that we define first n-dimensional boxes, which are basically just intervals on each of the dimensions. And then you just take the Cartesian product of those intervals. And so the best measure is just the product of b minus a for each of the dimensions, where b is basically the upper bound and a is the lower bound of your interval. And this gives you the volume. And of course, if one of the dimensions has no volume, then this is 0, and so the whole thing would be 0 again. And you can also do that for arbitrary sets. And the way you do that is basically just by covering this arbitrary set with boxes, and then you can just compute the volume of those boxes and your set. And the way of how the best measure is actually doing that, it is basically just defining this as the minimal volume over all sets of boxes which you can apply to any set. So basically, all possible ways of how you can cover this here with boxes, you consider them, and then you take just the minimal volume of that. So this is the mathematical definition of how you do it. In practice, of course, you would just take some way of how you compute the volume here. One way of how you actually cover the boxes here on a set. Okay, and now let's get back to what are actually zero measure sets in this case. So the Lebesgue measure, we call it here mu. It's defined relative to the dimensionality of the space. And so if we have a state space of dimension n, then we say that a set has zero measure if d is smaller or equal to n minus 1, whereby d is actually the dimension of the particular set, which is a minimal number of parameters to describe it. So if you have, for example, a line, then this would have been, is 1. You need 1 parameter to describe the line. A square, you need 2 parameters. A point, you need 0 parameters. And a cube, you would need 3 parameters. And so, of course, 3 is equal to the number of dimensions here. So this would not be a zero measure set, but all of them would be zero measure sets. And so this is how you can actually do that, but in n dimensions. And why did I actually even talk about zero measure sets? Why is that important? It is important for motion planning because the probability of sampling in a zero measure set is exactly 0. So if you have actually sets where you need to stay with your robot in one of those sets here, you can't explicitly sample them because, yeah, your probability of sampling them becomes 0. And this is in contrast to positive measure sets where you have basically a set where the measure is bigger than 0, and then the probability of sampling this actually becomes 1 if you just apply uniform sampling. So whenever you have at least some kind of volume in your space, then when you sample it, at some point, if you have an infinite sampling sequence, you will at least sample it at one point, and the probability of that is actually 1. So that is a big difference between them. And here are also some nice references for that if you want to know more about measure theory and how you compute measures. I want to now continue to do planning with zero measure sets to give you an idea of how this actually is done. And for that, I want to go back to like those 2D examples which I have often used. So here again, we have obstacles, which are those areas with lines, and we have a point robot. Point robot needs to go from a start configuration to a goal configuration. And what we have considered so far in the course was always solutions which go here through the free space, solutions which just connect them. But now we have this additional constraint that, for example, the robot needs to stay on the environment. And for this 2D case here, the equivalent would be that the robot is actually on the surface of those obstacles here. And so now we want to actually solve a problem where you want to go from green to red, but under the constraint that the robot always stays on the surface of the obstacles. And so, a practical application of that would be that you paint something on a wall, that you weld something on a car, or you wish something away from a tableau or something. And this, of course, creates more difficulty because now you can only move here on this area, which is just like a one-dimensional subregion here of the original state space. And as I said, this cannot be sampled because, of course, whenever you sample here, you will have 0 probability of actually hitting here a point on one of those lines. Okay, and more formally, we say that motion planning with manifold constraints works by defining a constraint function f, which goes from your configuration space Q to a space R, K, such that f of Q is 0 whenever K constraints are fulfilled. And this implies that instead of having this whole dimension, whole configuration space of n dimensions, you now have only m effective degrees of freedom in which you can move. So in our example here, you suddenly didn't have like 2 dimensions anymore, but only 1 dimension. And this, in turn, implies that you are now planning in an m-dimensional constraint configuration space. And so we will call that here x in this case. And it contains of all the points in your original configuration space, which when you project them using the constraint function, you get a value of 0, which means that all your constraints are fulfilled. And in this scenario here, we also call the state space Q the ambient space of X, because it's just basically the background in which you can plan. Okay, and so going back to our example, so X here in this case would be just the blue line segments, and Q and Q3 would, for example, be the green region here. And the difficulty, of course, is that sampling is not directly possible, of course, because you have a 0 chance to hit the constraints. On top of that, it's also not possible to do interpolation because you will almost always move into the ambient space. And so when you do planning with manifold constraints, you need to somehow address those 2 issues. And there are many different approaches. I just wanted to talk a little bit about 3 of them. One is relaxation-based, one is projection-based, and one is continuation-based. relaxation-based. The first one is basically the idea that instead of planning on this zero measure set, you say, okay, I want to plan on this zero measure set, but let's make it a bit bigger. Let's make it an epsilon measure set that would have a positive volume, and that is why you would find samples or have a positive chance of finding samples in this region, and then you can just do planning as usual, because now we have no zero measure sets anymore. And so the definition here is basically that instead of having this X space, which is equivalent to 0, you just now replace it by something where you are smaller or equal to some epsilon. And sampling is very simple. You just do uniform sampling and you reject everything outside of X epsilon. And so this is basically the same as you would have done before, where you had, for example, something inside of an obstacle. Right, and so what about interpolation in this case? Is that still possible? Or do you need to do something about it?
I would say it's not possible because I have like a corner of a room and I have a point on one wall and one on the other wall. The interpolation could be invalid.
Right, but couldn't you just remove it and consider it as an obstacle? So for example, if we go back here, you would say, okay, if I just directly connect them, then it's invalid, right?
Yeah.
Right. But what about if I just sample here something and I connect them, then it would be valid. And I could just say, okay, let's only consider edges which are exactly here inside of this region, they are valid.
Yeah, but like, if I have it on like on a corner, then interpolation doesn't work anymore. So I can't interpolate. Like, what's the question? Because I would say like it doesn't always work, so it's not guaranteed.
Well, yeah, it's definitely much harder, but it is not very different from what we did before. So you could just think about that there is a new obstacle here which covers the whole room, but it doesn't cover the small passage here. And so now we have basically just a narrow passage problem where you can also solve it.
Okay, now I see it.
Yeah.
Sure.
So yeah, depending on your epsilon, of course, that would be almost impossible to solve to doable. So you definitely have to like check what kind of epsilon you take, and it definitely depends on your application. But yeah, rejection sampling is possible and interpolation is possible. Then of course probabilistic completeness. Any idea if that is possible?
Since you said it's just a narrow passage problem, so I don't see why it wouldn't be complete.
So what would happen if, for example, I would have a path which goes very wide outside here, and there's maybe another obstacle here in between, and then you would have a path which is like solvable here, but you could not actually move it such that it's actually exactly here on this blue lines. So in that case, yeah.
It depends if we say that a path is feasible if it's inside the narrow passage or if it's exactly on the like contact surface. So
Yeah.
inside the narrow passage, yes, but
True, yeah. So maybe I didn't really specify this correctly. So of course, if you just talk about this space here, then yes, it's probabilistically complete. But this was just our approximation to the original problem. And if you solve this here, then you have no guarantee that you can actually resolve it into a path which goes exactly on the line, which is actually what we wanted in the first place. Okay, yeah. So, but of course, if your epsilon is small, then very often you can find a solution, and that is why this is actually a valuable approach to this problem. Okay, and the second way of how you can resolve this and how you can plan on those blue lines is basically by doing projection-based planning. So projection-based planning is basically that you just sample randomly as you did before, and every time you get a new sample, you project it down here on the line, and in that way, you have always samples on the line. And so what you need to do here is basically that you define a projection which goes from Q to X, and then you do projection sampling by just uniform sampling and projecting onto X. And again, my question, what about interpolation? Can you do it directly? Do you need to do something special about it? Yeah.
We still have the problem at a corner, right? Because we can't like take a shortcut.
Mm-hmm.
So I guess we can't do it instantly, directly. And I think it's also we also cannot do the trick where we just see the entire space except this narrow passage as a obstacle, because our path suddenly has the size 0.
Mm-hmm.
So we also can't really find anything there.
So you would say it's not possible at all?
I mean, you could do it probably, because if it's just a line, we can just interpolate on that line, but then we don't do it in our original state space.
Mm-hmm. Yeah, in the original state space it would not be possible. But yeah, as you said, so basically, so I think there are actually two ways of how you can do this interpolation, but you definitely have to do a different interpolation. One is that you interpolate on the line as you would do usually, and then for each point on the line you just project the point back onto your constraint space. That is one way of how you can do it, and the other way is that I think you can project them all at the same time down onto the line, which gives you a little bit more stability. And yeah, I think this paper here from Berenson, so there's a link in the end. This shows you how you can do this interpolation. One more question, probabilistic completeness. Do you think this is actually probabilistically complete if we can sample and interpolate?
Like, I don't see any reason why it shouldn't be.
Yeah, so it is probabilistically complete, but the proof is a bit more complicated. But you can also find it here in this publication. So basically, since 2009, we know that this approach here is basically probabilistically complete. Cool. So those were two ideas of how you can solve it. And the third one, which I want to talk about, is continuation-based constraint planning. And the idea here is that you try to come up with linear approximations to the space. And you do that at multiple points along the space. You basically compute those boxes here, which are approximations. And once you find an approximation in the goal region, then you have basically solved the problem. And so the idea here is that that you compute those piecewise linear approximations, which sometimes you can call a chart, and you use that to compute a cover or an atlas on the constraint configuration space. And then you do something which is called atlas sampling, where you just sample points in those linear approximations. And so basically you do two things. You build a representation of this constraint configuration space, and then you use this representation to actually do a bit smarter sampling of the space. And again, question, can you do interpolations there? Do you need to do something smarter with interpolation? Exactly, yeah. And probabilistic completeness? Do you think this is complete?
I would say it might depend on how we approximate the linear regions,
Mm-hmm.
because we can't be sure that we chose the regions correctly. And if we might not choose them correctly, we might not find a solution.
Mm-hmm. Yeah, I think this is definitely a concern, but there's actually a completeness proof in this paper here. And I think how they resolve it is basically that they allow approximations very, very close to each other and arbitrarily close to each other, so that in the end, you will always have like an infinite number of approximations, and that will definitely cover your whole space. Okay, and here's a small example of how this looks like when you have a small point robot in 3D space and you want to have it move only on the torus here, and you have not a explicit definition of your torus, and then this is basically a set here of linear approximations on which you can plan now. Okay, that is everything about constraint-based planning. Any questions? Yes?
Yeah, one major question, because like why don't we just sample on the constraint space and map that backwards? Like it seems this wouldn't want.
So yeah, of course, in this case, you could just sample here explicitly, but this whole approach was developed for cases where you can't do that. Because, for example, I don't know, you might have scenarios where your robot has to stay on a very specific path or something, and you can't just sample this explicitly, maybe. And so for those cases, you can actually do this approximation. But of course, once you have a way of how you can explicitly sample something, then this is not really necessary anymore, and you can just sample there, right?
Like, does this happen often that you can't sample in your constraint space?
Yeah, so I mean, for example, if you have context with the environments, then often it's a bit difficult to really sample the space. And especially explicitly, it's a bit difficult to do that. So there are definitely cases of where you would need that. Okay, and now we are at the very end of our lecture. So I hope you got something out of it. And in the end, I just wanted to advertise some thesis opportunities. So yeah, if you found this course interesting, we invite you to write a thesis with us. So requirements for that one would be that you can program good, especially C++ and Python, and I think linear algebra is also a good prerequisite. And then we have definitely a wide variety on topics, not only motion planning, but also robotics and combinations with machine learning. So for example, some topics we are currently pursuing is construction assembly, quadrocopter flight, solving physical puzzles with robots, and also a bit more on theory of motion planning. And we offer weekly supervision, and you will definitely be involved in cutting edge research, and there's also the possibility of, for example, writing a paper. And here are some examples of people which we supervised, which have not only written a master thesis, but they have also written a paper about it, and then this paper was even accepted at some good conference in robotics. And those are very different topics. So for example, Yannis wrote about belief space planning, where objects can either be present or not during runtime. Bora worked on solving physical puzzles, and he also used it to let a robot escape from an escape room. Francesco worked here on a space-time planner where we basically do motion planning but with time. And this was used for construction assembly. And then Marie worked on constraints for contact planning, especially with sliding contacts. So yeah, those were all very good master theses, and then they were even put into a paper. So this is basically, yeah, a very nice thing to have. Okay, and that is everything for today. Just to recap here again, we talked a bit about multi-robot motion planning, especially projections as a requirement for efficient planning. And then we talked about one-homogeneous planning, pebbles on a graph, conflict-based search. We talked about non-homogeneous planning, prioritize versus decomposed. And then finally, a very quick, brief overview about manifold constraints and zero measure sets. And yeah, since the exam is next week, tomorrow is a discussion round again. And I think it would also be good if you just post any questions on the forum so that everyone can see them and we can yeah, answer it there. Yeah, that's everything for today. Thank you for coming and see you at the exam.